this one as well. So I'm recording the second half of today's lesson, which is, let me just make sure that I don't crash again, which is the chain rule. All right, so 2.5, the chain rule. And you know, you remember that I was bugging you with that with compositions of functions, and I said things like this: f of x equals square root of 2x minus 2, and g of x equals square root of I'm sorry, not square root. So let's say this was what was this, something like 2x squared plus 2, and I asked you what is the composition of f and g, and the answer was the square root of 2 times 2x squared plus 2 minus 2. So basically what you do, you substitute this formula in for x in here, and that's going to give you square root of 4x squared, or 2 times the absolute value of x. All right, so this was the exam question. And you may have wondered, why did I bother so much about these compositions of functions and things like that? Well, the reason is because we want to make sure that we are at least minimally familiar with those when we discuss the chain rule. So what's the role of the chain rule? The role of the chain rule is to take care of problems like this one: f of x equals so something like 2x plus 1 squared, or something like the one earlier, square root of, that the sophisticated formula. So when you have this kind of function, how do you do the derivative of that? Well, the trick is to think of it as the composition of two functions. So now this is the composition of a square function, the function that squares everything, right? So x goes to x squared times the function 2x plus 1. So this particular function is this particular approach leads us to look at the more general problem when you have a function f circle g and you want to calculate the derivative of that. And I'm not going to show you why the derivative is this one here, but just to let you know that the derivative is not a very simple formula. You got to think carefully here. So the derivative is called the chain rule. Why? Because you can think of this as a chain of functions. You could have as many as you want: f1, f2, f3, So you could have a chain of functions that you do compositions of. All right, so this would be a chain of functions. And when you do this chain, you want to treat the chain, when you do the derivative, you want to treat it link by link. In other words, what I'm going to do, I'm going to always start from the left, because we read and write left to right. So always start from the left and say the first function, the derivative of the first function, circle G. So you hit the first one by a prime, the first link by a prime, and you leave the other one the way it is, a composition, and then you say times. And folks, this is times as in times the product. Times, and then you drop the first one entirely and you do the derivative of the second one. So this would be the derivative. In concrete terms, this, if you want to write in terms of x, this will be f prime of g of x. Oops. F prime of g of x times g prime of x. All right, so this is the derivative of f circle G. And this derivative is, so it's very important that we understand this process and we apply it to several concrete situations. So I'm not going to insist too much on this theoretical aspect of the chain rule. So this is called the chain rule. And what I'll do next, I will insist on some practical aspects of the chain rule, kind of see how we apply the chain rule to concrete situations. And then here's how it goes. Here's how it goes. So the problems that we want to do here are problems like, for instance, number one. And number one from our book says, from 2.5, says y equals the cube root of 1 plus 4x. And the question is asking, find the derivative of y. Now, before we do that, let's recognize the aspect of this problem. So this is the 1/3 power composite with the function 1 plus 4x. So when we do the derivative, we do the derivative as 1/3. Why is it the 1/3 power? Well, because the cube root of something is the 1/3 power. So this would be 1/3. That thing, the power, the 1/3 power, the derivative of that is 1/3 the thing to the negative 2/3, 1/3 minus 1. I'm going to put in here 1 plus 4x because the composition stays the way it is, the second function stays the way it is, times, and then I'll say 1 plus 4x prime. And this is going to end up being, for the final result, 1/3 times 1 plus 4x to the negative 2/3 times 4 from 1 plus 4x prime. Or if you combine the constants, 4/3 times 1 plus 4x to the negative 2/3. So this is the final result. Now let's analyze and let's see what happened here. So here's what happened here, folks. I'm going to increase the size here, kind of want to analyze this. So we're done with the problem. But here's what happens when we look at the overall picture. We started with this one with 1 plus 4x to the 1/3, and we primed that. And what we did, we treated this as if we were just simply doing the derivative of a power. So 1/3, 1 plus 4x to the negative 2/3, because 1/3 minus 1 is, excuse me, is negative 2/3. And then we say, but wait, this is not over. So if this was simply just x over here, then I would say that's it. But if this is not x, I would say times that thing primed. Of course, I could say here times, even when it's x here, I could say times x prime because x prime is 1. But over here, it's crucial that we also say times 1 plus 4x, the thing that was raised to the 1/3 prime. This is the formula, and then again, this is going to give you that. So this is kind of maybe your first, if you haven't taken calculus in high school or something, this may be your first time you see the chain rule applied. So don't worry, we're going to do a bunch of exercises here to kind of ease to kind of get everybody familiar with the chain rule. That's a very, very important rule and very easy to apply, really, folks. It's just applying the previous rules, the ones that we learned for powers, for trig functions and such, and keeping in mind that if the argument is a little more complex, if instead of raising x to the 1/3, I raise something more complex, I keep in mind to take the derivative of that and multiply the whole thing at the end. So that's kind of the philosophy here. All right, so So this is our first example. Our second example will be number 2 from the same lesson from 2.5. These are all assigned problems, folks. So y equals 2x cubed plus 5 to the 4. And we kind of saw what to do with these kind of problems. So y prime, folks, is going to be, use the usual. So think of these as an entire, as just a single thing. If you had x to the 4, how would you do that? You would do 4x cubed. Well, it's the same thing here. So you will do you will do 4 times 2x cubed plus 5 cubed, right? And then you say times this argument from here, which is slightly more complex, but not a problem because we just say times that thing prime. And that's going to give us a very simple answer. So we get 4 times 2x cubed plus 5 cubed times, and this guy here can be taken care of easily. So 2x cubed prime, is going to be 6x squared, folks. Yeah, 2 times 3x squared. So 6x squared, and I can stop here because I have would be plus 0, 5 prime, that's just 0. So this is going to be 24 times 2x cubed plus 5 cubed. 24, I'm sorry, x squared. Let's put x squared over here as well. So I like to collect the powers of x and the constants in front of a more complex formula. This would be the final answer. All right, so that's our second problem. Our third problem is in the same spirit, except that we now have to deal with some trig functions, which, it's not a big problem either. Y equals tangent of pi x. Does that look good, folks? All right, so when you have tangent of pi x, we are going to say the derivative. Look here, the same structure. So if we had tangent of x here instead of pi x, the derivative will be secant squared x, right? So this is the same sort of thing, secant squared of pi x this time around. And then we're going to say times, because we didn't have x, we had pi x. Well, this guy would have to be taken separately and prime. And this is the answer. So pi x prime is pi, and I'm going to put that in front. Pi times secant squared of pi x. And this is a very useful exercise, folks, not particularly this function tangent, but in trigonometry and later on when we do antiderivatives, it's going to be very useful to remember. This is what I want to point out next. Things like, say, sine of 5x. When you prime these sort of things, the result is going to be, of course, sine prime. Yeah, this can be thought as another example. Number 4 example here. Sine prime, which is cosine of, that 5x times 5x prime. And that's going to end up being, cosine of 5x times 5. And that is going to be, or even better, let's write 5 in front. So 5 times cosine of 5x. All right, folks, so this is going to be the derivative. This is something that you very often will see in calculus when we do derivatives of something like this, not just sine of x, but sine of something more complex. Okay. And finally, let's do numbers 5 and 6, and let's see that there is a difference between those two problems. So this is what I'm going to end the lesson with 5 and 6. These are problems 5. So first problem 5 from 2.5. And in this problem, I need to do the derivative of the square root of sine x. And for this problem, again, I need to recognize the structure of a problem, folks. So the structure of a problem is sine x to the 1/2. So what composition do I have here? I have the 1/2 power, and then I substitute sine x in the 1/2 power. So this is going to be, y prime is going to be 1/2 sine x to the negative 1/2, which is 1/2 minus 1, right? And then times sine x prime. And this is going to be, folks, 1/2 sine x to the negative 1/2 times, and sine x prime is cosine x. If we write this as a fraction, and a lot of people like to write this as a fraction, that's going to be cosine x divided by 2 times. So why am I saying divided? Because of a negative exponent here, 2 times sine x to the 1/2, which is the same as the square root of sine x. So look at that. We started with something mild over here, and we ended up with this kind of monstrous quantity over here for the derivative. So this is the derivative of square root of sine x. Finally, our last problem today will be number 6 of section 2.5. And number 6 says we gotta do y equals sine of square root of x. Okay, so now pay attention here. This is different. This is quite different. So, so the derivative is going to be, now let's pay attention at the structure of this problem. This is sine of square root of x. So instead of sine x, I have sine of square root of x. Again, it's not a power of sine. It's the argument here that is problematic, so it's different. So if I had sine x instead, I would easily know how to do that. That will be cosine x, right? Well, that's exactly what I'm talking about here. So I am going to say cosine of square root of x, that's the derivative of sine, times square root of x primed. All right, so square root of x primed is very easy. I'm going to do that separately, is x to the 1/2. So when we prime that, and we're going to get 1/2 x to the negative 1/2. So this is going to end up being cosine of square root of x times, and we're going to have 1/2 x to the negative 1/2. But if we still want to have square roots, well, then we're going to write cosine of square root of x, the one that was here, and then the rest of it at the bottom. So we have 2 already at the bottom, x to the negative 1/2. Flip over that thing is going to be x to the 1/2 at the bottom, or square root of x. So cosine square root of x divided by 2 square root of x. That is the final answer over here. So, so there's a significant difference between this one problem and the one earlier, folks, where you had the square root outside the sine function. So the square root was the prima donna here, let's say, in this problem, the star of a show. That was the star of a show, and then the sine was under the square root. Now, when you look at the next problem, the square root plays a secondary role. So the star of a show is sine. So sine, and then you change the argument of sine at the beginning. All right, so that's why these two problems are different, and the answers obviously are different. So they're not the same problem. All right, folks. So this is it for this short half